Welcome to the UCT IT showcase for the orchard structure classification on this project. The team that did this was comprised of Jonathon Everatt, Piero Puccini, and Chelsea van Coller, and we were supervised by Associate Professor Patrick Marai, with Professor Tommy Mayer as the second reader. Food security is a large problem faced globally with many factors influencing it, such as high population growth, global warming, and poor agricultural systems. Agriculturalists developed the concept of precision agriculture to produce larger amounts of food whilst facing land constraints. This is a practice that assists farmers in making management decisions through abstracting data from technology, in this case drones. This allows farmers to monitor their crops more closely and efficiently. This project will determine whether template matching, image comparison, or Hough Transform are useful algorithms for detecting planting patterns present in an orchard. Farmers organize their orchards into different planting patterns to assist with many aspects of farm management, such as efficient irrigation and cross-pollination, accessibility for farm equipment, and for ease of harvesting. These structures affect the system management recommendations produced through the precision agriculture and assist in providing a strong preliminary for detecting trees, as well as identifying locations where trees are missing. There is no one correct answer for which planting pattern to use, so using precision agriculture to detect these patterns in orchards and then accurately determine the most suitable structures going forward based on the real-world data. The project had two sets of goals to accomplish. The primary goal was to correctly identify the planting patterns present in GeoJSON data sets of orchards that was given to us by the company Aerobotics. The secondary goal was then to extract parameters about the planting patterns that we had detected. These parameters include, but are not limited to, the coordinates of corner trees and the spacing within and between rows. We developed our own in-house idealized data. The real-world data was supplied to us by the company Aerobotics. We were given 7 datasets of orchards with an aerial TIFF image and a GeoJSON file containing polygons of trees that they had pre-detected at different confidence intervals. For the project, we read in the GeoJSON files and calculated a centroid of polygons that we used for different approaches to the project. Template matching is a process of determining the presence and/or location of a subimage, called a template, in a larger image. This was hypothesized as a good candidate for the orchard structure classification project because the planting patterns we were using were made up of repeating geometric shapes, and those shapes will constitute the templates. This approach was also successful in detecting planting patterns in the real-world data sets we were given under the assumption that the rows were straight and not curved. However, it was limited as the technique could not differentiate between two very similar patterns. The template matching process has 3 stages to it. The first stage is parameter extraction for the secondary aim, and to detect those scale and rotation parameters that are necessary for the template matching algorithm. The data set is also broken up and graphed with multiple sub-images for template matching efficiency and accuracy. The second step is the application of the OpenCV template matching algorithm, which generates templates at detected scales and then scores them based on the number of matches and correlation scores of 0.1 increments. The final step evaluates the scores and penalizes certain templates based on their characteristics. For example, if the intra and inter-row spacing are very similar, patterns similar to the rectangle pattern will be penalized because it's unlikely that they are the pattern present. Then determines the present pattern and outputs the pattern and parameters that were detected. Row detection was used to solve for the problem of rotation that template matching algorithms face. It was then extended to also solve for intra and inter-row spacing. A variation of it was also used to try solve for the number of rows, ditch count, and trees per row. However, it failed, and a more complex row detection algorithm would be needed to solve for the parameters. The algorithm was built by using KD trees to find the closest points and then measuring the angle between points to see if they fall within the same row. You can see on the right that the detected points are in red. The algorithm did not always detect a full row, but it detected enough to solve for the rotations. The spacing within the row was the intra-row spacing, and using the rotation, we could calculate the nearest point that wasn't within the row and average the spacing between them for the inter-row spacing. The corner tree coordinates were the min and max x and y position of the points, and the tree count was just the number of points that we were dealing with. Each template was scored to determine which was representative of the data set. The scoring was done based on the number of matches and correlation scores, with each correlation being worth twice the level below it in 0.1 increments. The templates were also penalized based on the spacing, as if the intra and inter-row spacing were similar, the rectangle and triangle patterns were penalized. Also, it was the square and hexagonal patterns that were penalized. The highest score is the most likely pattern. but if any pattern scored higher than 75% of the max score, it was included as a possibility due to noise. So we can conclude that the template matching approach was successful in the primary goal and partially successful in the secondary goal, extracting 4 of 7 parameters. It faces problems when dealing with similar templates that both match to the dataset, as you can see with the square and quincunx patterns both matching a square pattern. However, this was accounted for using penalization of the most common patterns, and there is a lot of room for improvement using more complex template matching techniques and row detection algorithms.
This slide gives an overview of the Hough Transform, which is a computer vision approach which is used to identify planting patterns and the secondary parameters. This transformation is from the Cartesian space to the Hough space, and one of the main features of this approach is its ability to detect a line regardless of how fragmented it is. The data is in the form of real data and stylized sample data. The real data is in the form of GeoJSON files of tree polygons at different interval levels. Centroids are calculated from these polygons, and these are saved as an image file. The sample data is just stylized data, which was created to imitate the real data centroids, and this was used to test the process as parameters are known. Image. Prior to the Hough transform being applied, pre-processing is needed. This is first done by applying a canny edge detector to the image of tree centroids, as an edge map is input to the Hough transform. After applying the edge detection, pixel reduction is applied to increase the accuracy of the Hough transform. These can be seen on the images to the left. Prior to the Hough transform being applied, pre-processing is needed. This is first done by applying a canny edge detector to the image of tree centroids, as an edge map is input to the Hough transform. After applying the edge detection, pixel reduction is applied to increase the accuracy of the Hough transform. These can be seen on the images to the left. Findings from the application of the Hough transform. The Hough transform was successful in determining the main row orientation. Variability of centroids, however, within the rows led to false positive rows being identified, even with line filtering being applied. Ground noise for some orchid data also created false positive row identification. Missing points at corners for higher confidence levels in the datasets led to some corners not being able to be identified. So overall, the Hough transform was good for determining the main row orientation. It could find rows in one direction, but not in the secondary direction due to centroid sporadicity. It may be quite useful to be used as a precursor to template matching techniques.
My paper discusses using the Hausdorff distance to assess the similarity between 2 point sets. Thus, all polygon data taken from the trees is converted to point system through using the centroid of each tree. This is then manipulated to provide easier matching for the Hausdorff distance. There are different data sets produced that can be matched to the different patterns we are trying to find between the trees, which can be seen on the left. In literature, we find 3 different variations of the Hausdorff distance. This is the partial, exact, and average Hausdorff distance. In our findings, we discovered that the partial distance was too lenient as it matched too many different patterns. The exact Hausdorff was very stringent as it could not discover all the patterns, and the average Hausdorff distance was discovered to be the best approach and managed to match patterns correctly. However, this is a very expensive algorithm as it needs to find all the nearest neighbors for each point. Thus, a CKD tree was used, and this speeded up efficiency effectively. The matching algorithm was the next element of this paper. Effectively, the model sets and the point sets needed to be matched to one another to find the best Hausdorff distance value. Thus, the data was translated incrementally through the model, and at each translation a rotation needed to occur to find the lowest Hausdorff distance. This was extremely expensive and not efficient. However, in future iterations, rotations could be omitted by using the Hough transform. Overall findings for the paper are that the average Hausdorff distance is partially effective when identifying pattern shapes within the orchard data. There are, however, efficiency problems which makes this algorithm not ideal. When identifying the missing trees within the data, this approach may not work effectively. There are also problems with identifying the boundaries between the trees, as too small a boundary may result in an incorrect pattern being detected.